Hey everyone, so we've all seen AI models do some pretty amazing things lately, right? But behind the scenes, there's this invisible barrier, this memory wall that's been holding them back. Today, we're going to talk about the genius algorithm that didn't just put a crack in that wall, it completely blew it to pieces. So let's start with a really simple question. Why can't a model like GPT just, read a whole novel in one go to answer a question? Seems like it should be able to, doesn't it? Well, the answer is this nasty bottleneck that just gets worse and worse, exponentially worse, the more text you try to cram into it. You see, at the heart of pretty much every large language model is the transformer architecture. And the engine that makes the transformer go is a mechanism called self-attention. It's how the model figures out context, which words matter most to which other words. It's incredibly powerful, but it has one massive, and I mean massive, problem. And that problem has a name: quadratic complexity. This is the scaling wall, the fatal flaw. It means if you double the length of your text, the memory and compute you need don't just double, they quadruple. So trying to process a chapter is hard. Trying to process a whole book, the cost becomes just completely ridiculously impossible. So you're probably thinking, okay, just get bigger, more powerful GPUs, right? Just throw more hardware at it. But here's the thing. The researchers behind FlashAttention realized that everybody was looking at the wrong problem. The real bottleneck wasn't the raw number-crunching power at all.
Turns out the issue isn't how fast the GPU can do the math. It's how fast it can move data around. Think about it like a world-class chef who can chop and cook at lightning speed, but their pantry is a 5-minute walk away. All their time is wasted just running back and forth. That's the I/O bottleneck, and it was slowing these super powerful models to a crawl.
To really get this, we gotta look under the hood of the GPU itself. It has two totally different kinds of memory. You've got this huge ocean of high bandwidth memory, or HBM. It's massive, but it's actually kind of slow to access. And then you have this teeny tiny little workspace right on the chip called SRAM. It's small, but man, it is blazing fast. We're talking over 10 times faster. And that speed difference, that's the whole game. So let's stick with our kitchen analogy. The GPU is the kitchen. That huge, slow HBM, that's your pantry. It can hold all the ingredients you'll ever need, but it's a long, annoying walk every single time you need to grab something. And that tiny, fast SRAM, that's your countertop. You don't have much space, but anything on it is right there, ready to go. So the way standard attention worked was like the world's most inefficient chef. This chef would walk all the way to the pantry, grab one ingredient, walk back to the countertop, do one tiny little thing, and then, and this is the truly insane part, he'd walk the partially mixed bowl back to the pantry just to store it before getting the next ingredient. It's just a constant, maddening traffic jam of pointless trips. And this is what the FlashAttention authors pointed out in their paper. They said, look, the missing piece here is making these algorithms I/O aware. Stop focusing only on the math and start paying attention to all those slow, expensive trips between the different levels of memory. And their first really brilliant idea was something called tiling. It's a simple concept, really. Instead of grabbing one thing at a time, you just grab a whole batch of things that you know you're going to need. It completely changes the workflow. So now let's look at the FlashAttention master chef. This chef goes to the pantry once and brings a whole tray of ingredients, a block or tile of data, back to the countertop. Then they do all the work right there in that super fast workspace. They mix, they chop, they cook, and only when the final dish is completely done do they take one single trip back to the pantry. All that back and forth, it's just gone. Okay, the second trick is maybe even more clever. It's called recomputation. You see, the inefficient chef, to remember what he did, would write down every little step on a note and walk that note back to the pantry for storage. The FlashAttention chef realizes, wait a minute, it's actually faster for me to just redo that simple little calculation than it is to take that long walk to the pantry just to read my note about it. It's brilliant. It saves an entire trip. And the result of these two ideas working together? It's a 9-fold reduction in those slow reads and writes to HBM. 9 times! The traffic jam is cleared. The chef can finally cook. So, does this whole kitchen analogy actually work in the real world? Oh yeah, big time. Just look at this chart. On a powerful A100 GPU, FlashAttention is consistently 2 to 4 times faster than the old way. And see those blue bars? That's when you get even smarter and fuse other little kitchen jobs like masking or dropout into that same session on the countertop. The speedup gets even better. It's all about fewer trips to the pantry.
A 4x speedup on one part is cool, but what does that mean for the whole process? For training an entire model from scratch? How about a 3 times faster end-to-end training time for a model like GPT-2?
And let me put that into perspective for you. A standard implementation would take 3 weeks, 21 days to train. Even a highly optimized version took almost 12 days. With FlashAttention, less than a week. We're talking about going from weeks of waiting to just days. That's not just an improvement, that's a total game changer for research.
But believe it or not, the speed is only half the story. Because FlashAttention avoids writing all those intermediate steps back to the HBM pantry, it's also up to 20 times more memory efficient. And that is the real magic key.
This radical memory saving is what finally lets us answer that question from the very beginning. By smashing that quadratic memory problem, FlashAttention is the thing that finally unlocks these huge context windows. It lets our models go from reading a paragraph to reading an entire document. And longer context doesn't just mean reading more. It means building smarter models. We're seeing higher quality across the board. But the truly wild part was seeing transformers tackle problems that were literally impossible before. For the first time ever, a transformer could beat random chance on the Path X challenge, which involves a sequence length of 16,000. Then they pushed it to Path 256, a mind-blowing 64,000 token sequence. Before FlashAttention, this wasn't even in the realm of possibility. So when you zoom out, you realize FlashAttention wasn't just another clever trick. It was a complete paradigm shift. It forced everyone to rethink where the real problems were. And because it was so effective, it became a brand new, foundational building block that pretty much every major AI company and open source project now relies on. If you look at the history of these models, you can really see its impact. The Transformer was born in 2017. We got some nice optimizations after that, but 2022, with the arrival of FlashAttention, that was the real revolution. And they didn't stop. FlashAttention 2 came out just a year later, pushing everything even further. It all comes back to this quote from Samuel Johnson, way back in 1787. The true art of memory is the art of attention. The researchers who built this realized that to fix the AI memory problem, they had to fix how the machine paid attention, not to the words, but to its own memory. FlashAttention worked because it optimized the conversation happening inside the GPU between its fast and slow memory. And that really makes you wonder, what's the next great conversation in AI that's stuck in a traffic jam? Is it the one between different GPUs, or between the model and the vast ocean of data it learns from? Where's the next bottleneck we need to break? Thanks so much for watching. We'll catch you on the next one.